Welcome back. This is CS4510 L02B. It's called the Powerset construction. So what we're going to do in this second half of today's lecture is we're going to compare and contrast the DFA to the NFA. So recall we talked about the DFA. LDFA is a class of languages which have DFAs to decide them, right? So a language is said to be an element of LDFA if there exists a DFA for it, right? It's decidable by a DFA. Now, we can equally define a class called LNFA, which is the class of languages that have NFAs to decide them. What do we think the relationship is between LDFA and LNFA?
Since all DFAs are NFAs, then it should be one is, subset of another, right?
We know that much. Let's prove it. We don't really need to prove it. It's kind of basically every DFA is an NFA. The generalization of non-determinism is a generalization. All a DFA is, if an NFA doesn't use any of its superpowers, then it's just the same thing as a DFA, right? So the generalization just means that everything that's decidable by a DFA is also decidable by an NFA. But let's just be a little explicit and write it down. We prove, again, to prove that A is a subset of B, you have to prove that for all X is an element of A implies that X, for all X, such that X is an element of A implies that X is an element of B, right? So what we're going to say is let L be an element of LDFA. By definition, then there exists a DFA to decide L. It accepts when it's supposed to, it rejects when it's supposed to. Notice this DFA is also an NFA. So since there exists an NFA to decide L, if there exists an NFA to decide L, then by definition, then L is an element of LNFA. Thus, since this is for all L, we have proven that LDFA is a subset of LNFA. QED. Not particularly needed, but why not? Just warm ourselves up. The next question is, what else do we know about the relation? Any questions on this argument, first of all? Again, non-determinism, simply generalization. Every DFA is automatically an NFA. Every C program is technically a C++ program, right? I don't remember, but same thing, right? What else do we know about the relationship between DFAs and NFAs? So we know immediately, by the fact that we've proven this containment, we've already proven something nice. It does not look like this, okay? It doesn't look anything like that. It's got to be one of two cases. It's either the case that they look like this, where one is contained in the other, or it must be the case, this can never happen, right? So it must be this case or this case, where they're both just equal to each other, right? So what do we conjecture? Do we conjecture, this is an open-ended question, that they're equal or not equal? Yes?
They're not equal.
Why?
I'm not sure if this is totally correct, but the size of the DFA is 2 to the n, and the amount of NFAs that can represent the DFA, those sizes is n.
That's a pretty good remark. But when in the context of this class, we're not going to care about, at least in the first half, any kind of optimality. So you're right, in fact, and we've given several examples where it appears like the NFA can do it with A plus B states, but then the DFA takes A times B states, something like this, right? So it's like, okay, the NFAs are smaller. But think of the states of an NFA like lines of code in a program. So like, we don't really care if one program takes longer necessarily. We just care right now if there even is an NFA for it. So it is definitely true that the problems that appear to have languages that have NFAs and DFAs for them, that the NFAs do appear smaller at least. That's definitely true. And this is not, there's not a correct answer to this question, but it's an open question. Do we think that NFAs are strictly stronger than DFAs in a possibility sense? In that there is two cases. One, there is some L, which is decidable by an NFA, and then not decidable by a DFA. Like, there is no DFA at all for such a problem, right? Or case two, which is that L NFA, everything decidable by an NFA is also just decidable by a DFA somehow, right? Yes?
So now I'm thinking that the bottom one is true because all DFAs can be represented by an NFA.
Correct. So every DFA does have an NFA, but the question is, does every NFA have a DFA? And again, open-ended question, not a right answer yet. I just want to get people's intuition on. Yes?
Intuitively, I want to say no. This
Okay.
feels like P versus NP.
Yeah, good thing to notice. So P versus NP is without getting into formal definitions about things, NP does not stand for not polynomial. It stands for deterministically verifiable, right? You probably learned a verifier definition in 3510. But actually, the N is like, why is it called NP then and not like BP or something, right? N is not polynomial. In fact, NP is the non-determinism that we've described here. We'll talk about this in much more detail later. We'll have at least 6 lectures on the P versus NP problem. But it's interesting because, and one of the reasons that makes the P versus NP problem so mysterious is because it's like, depending on how you give non-determinism to things, it's either a really easy question or a really hard question. So this question is unsolved. We don't know how to solve this one. Like, as in the theoretical computer science communities, we're not totally given up, but we're kind of lost. We have no real strategy. There's no plan right now. There's many failed plans, but no one's really making good progress on this problem. In contrast, this is a problem that was solved in the 60s. So we do know what happens if you give non-determinism. We don't know what happens if you give non-determinism to a polynomial time computation, like a real program. We'll talk about that later. But we do know what happens when you give non-determinism to an NFA. We can actually prove it. It's one of these two cases. But your intuition says that we probably think P does not equal NP. So you think probably the NFA does not equal the DFA?
Yeah.
Okay. Any other poll? Just a poll for the audience. Any other intuitions? Yes?
So you said we're not focusing on the size of the problem, but the fact that the sizes of the problems are finite, is that correct?
Yeah, exactly.
Would that mean that then, I'm not sure how that applies, but that's my intuition is to look into that.
I'm going to use that as a joke when we do the actual thing, because that's basically the answer, right? Any last polls on the question before I tell you the answer? Oh wait, the answer is that they're equal. They're actually not equal. So it's not that it's false that they're not equal. They are in fact equal. Every NFA has a DFA. Now that doesn't mean that every NFA is a DFA, because NFAs all have these weird powers. What it actually means is that every NFA has an equivalent and different DFA. There is a DFA for every NFA. Now, we'll prove that in just a second, and that's why it's called the Powerset construction. Last time we did the Cartesian product construction, we made one DFA simulate 2 DFAs at the same time. This time, we're going to create a DFA which simulates an NFA. Before we get too meaty into the details, let's talk about sort of the idea behind it, right? An NFA can be in a superposition of states. It's in multiple states at the same time, right? Something like this, okay? When you are reading an A, you're in like these states, right? So let's say an NFA is in several states at the same time. Many states at the same time, right? it can be in any kind of possible combination of states at the same time. But if the DFA has n states, how many possible sets of states could the NFA be in? Excuse me, let's say the NFA has n states. In how many states at the same time? Like if you were to pause the computation of the NFA, it currently has its cursors in many states at the same time, right? How many possible ways could it have a hold onto the states it's currently at that step? Yes.
-1.
Well, let's just say 2 to the n at least. It is actually, as we'll see, the -1, are you saying that because of the empty set?
Yeah.
It turns out that a NFA is allowed to be in 0 states at a time when it's implicitly rejecting. That's the convention we'll take.
I see.
Yes, that's the convention we'll take.
Yeah.
So, and in fact, that corresponds to being in the empty set of states at the same time, right? So it could be in 2 to the n states. Now here's the comment you made. 2 to the n, if n is finite, then 2 to the n is finite. That's still a finite number of states. It's more states, but it's still a finite number of states. So we can use the f in DFA, sorry, that's the wrong f. So the NFA has n states, it could be in 2 to the n sets of states. So we make a DFA with 2 to the n states. And we can do that because the DFA has finitely many states. Each state of the DFA is basically going to correspond to a possible set of states of the NFA, right? To give you one last piece of intuition, suppose you had a bacteria or a mold growth or something in a petri dish, okay? And let's suppose at some initial state, we are at this set of states at the same time, okay? Let's say we advance a step, and then we're at, let's say, something like that, okay? We advance a step, we're at that new set of states. Those are the states that the NFA currently has its fingers in, right? Then we advance one more step in the NFA, and then we're at those sets of states or something, right? Now, the NFA is in many states at the same time. It's non-deterministically moving between states, and it's evolving from this set of states to a different set of states to a different set of states to a different set of states, non-deterministically between sets of states. But the way it goes between sets of states is actually deterministic. So what we're going to do is really make the DFA that instead of doing this kind of weird thing, it just does this. Right? That's basically going to be your DFA to simulate the NFA doing this kind of weird, funky thing. Does this diagram make any sense at all? You guys understand what's going on here? Okay, good. That's all the Powerset construction is. We'll talk, the rest of the data will be spent upon how to de-non-deterministify an NFA and make it into a DFA. One last thing I can comment about the Powerset construction. This was invented in 1959 by Rabin and Scott. And I mentioned that because they won a Turing Award for it in 1972, 73, 79, something like this. It's worth mentioning because the Turing Award is the biggest, it's like the Nobel Prize in computer science, right? They gave it in 2022, I think, to the guy who invented Ethernet. You know, it's like a big deal. It comes in many areas. I think recently it was to the guys who did reinforcement learning, I think last year's. And the time before it was Avi Wigderson. Anyway, big deal. But it shows you how far computer science has come because what can be, what would be granted a Nobel, equivalent to a Nobel Prize in the 70s can now be taught in an undergrad lecture in 30 minutes, right? But that's how far computer science has really come. This technique that they came up with is what they basically got. The invention of non-determinism. The definition of non-determinism, as well as this technique, is what they were awarded the Turing Award for in the 70s. So, let's proceed with the technique. Questions on that?
How do you do the epsilon state?
Let's talk about that right now.
The epsilon transition.
Yeah. So the first problem is exactly the epsilon transitions. how do you do epsilon transition? So let's say you're in a state Q0. Let's say you have something like this. Okay. Now, anytime you enter the state Q0, you also technically enter Q1 and Q2 for free. So if you ever are in Q0, you're also in Q1 and Q2, right? So we need some way to like define or represent this. So what we define is, we say that the reach of Qi, and reach is a function, it returns a set that contains Qi and any state reachable from Qi only via epsilon transitions. So the reach of a state is that state with anything else that you can get to for free, only using epsilons. So in this example, the reach of Q0 would return to us Q0, Q1, and Q2, right? And in fact, if Q0 is the start state, what you can really think of this as is that if I have a system like this as a fragment of some larger NFA, what this really means is that I could start from Q1 or I could start from Q2. Q0 isn't the actual start state. It's just one of my 3 start states, something like this, right? So now we need to define the Powerset construction. So let n be an NFA of Q, sigma, Q0, delta, and F. We give a DFA D. Such that D is Q prime, sigma, Q0 prime, delta prime, and F. Now F prime. Importantly, the DFA will be deterministic. The NFA will be non-deterministic, right? But we're gonna basically convert the NFA into an equivalent DFA, right? So let's just define the parts of our DFA. And again, we'll do the formal definition and then we'll do an example that shows how the construction works. The states of our DFA should be what? Yes?
The power set of the states of the NFA?
Yes. We're going to make one state in our DFA per possible set of states in the NFA, okay? Sigma is going to just be that. We're just going to ignore that. What should the start state of the DFA be?
The reach of the start state of the NFA.
Yeah, it's not just going to be the start state of the NFA, but anywhere else you could start here. So again, in the example here, you could start at Q1 or Q2 in this fragment of an NFA. So it's actually going to be the reach, not just Q0, but the reach of Q0, right? Okay. Now the hard part, the transition function. It's going to be deterministic. So how do we do this? Let's suppose we have a set of states in the NFA. So let S be an element of the power set of Q, right? Or that S is a subset of Q. What we want is our transition function, this will be delta prime, right? Delta prime is going to take this set of states and let's say symbol A, for A is in the alphabet, and it's going to, we want it to move to a set of states. How should we can define this mathematically. How should we do this, right?
The union of all states obtainable?
Yeah, I mean, basically. So let's union over, I'll give you some hints, because this is not, no one's going to come up with it. Q in S. So we're going to union over each element in there. Yes?
It would be the union of all the reach states of Q.
It would be the reaches of, not of Q, but after we took the symbol A. Yes?
What is A again?
Just any symbol. Suppose it's just a letter of the alphabet.
One of the inputs.
Exactly.
Oh,
So if it was the epsilon, it would just be reach of Q here. But if it's not epsilon, it would be what?
reach of A.
Almost. No, reach would work on a state. I'll tell you, it's going to be the other transition function.
QA.
Yes, thank you. Right. So for example, if Q0, Q1, Q2, what we do, if that's what we have in the NFA, what we do in the DFA is we go Q0, like that. Right. And the union definition is a little cumbersome, but that's basically what it allows us to work, right? Final thing, the final states. Now, this is difficult to define mathematically, but in terms of like what it should be in English, like in natural language, what states of the DFA should be accepting? And again, this is a DFA constructed to simulate the NFA.
All sets that contain F.
Yes, actually an element of F. So cumbersome to define, here's what I have. If S is a subset of Q such that the old final states of the NFA intersect with S are non-empty. So as long as they contain an accept state, then we make it accepting. In the previous example, let's say Q1 was accepting. This is an accept state because it would contain an accept state. And the definition of non-determinism is if you reach an accept state, if there exists an accepting computation. So we would make this accepting because one of them happens to be accepting. The others happen to be rejecting, doesn't really matter. But as long as one of them is accepting. So that's why we do unions and stuff. Yeah. Questions on the formal definition before we just get to the example?
So this is basically a manual breadth first search.
That's a kind of, but the difference is, and we don't really care about time of the NFA or the DFA, but yeah, kind of we've like unrolled the NFA to be a DFA, so it still takes exactly, let's say, depth n.
Of course.
Yeah, so you don't have to like backtrack and do something. So the representation of the NFA is less concise. It does take exponentially more states. Now we'll argue on why it does, if it can always be less than that or not, but kind of, yeah, that is a way to think of that. You unroll the NFA into a DFA so you don't ever have to backtrack in the computation tree. Let's do an example. Any more questions on the formal definition, which will become more clear as we do the example? Okay. So let's suppose that our NFA is as follows. What strings does this NFA accept?
Ends in 2 A's.
You go A, B, you guess the prefix correctly, then you transition when you're exactly to a way, you go A, and then you accept. Many other rejecting computations paths on every word, but it'll accept exactly only those words that end with AA. Now let's convert this to a DFA given the process. So I'm going to, instead of drawing a set of states like this, I'm just going to use the numbers, so it's simpler. Let's call this Q0. Let's call this 01. Actually, I think I need some room. This is going to be 012. Let's put 02 out here. Let's put 1 here. Let's put 2 here. Let's put 1, 2 here, and we'll put the empty set state here. Something like that. Which state is starting in the NFA, in the DFA? This is 8 states of our DFA corresponding to 2 to the 3 subsets of states of the NFA, right? So this is our DFA. Which state is starting of the DFA?
0.
Let's say we're at Q0 and only state Q0 in the NFA and we see an A. Where should we transition?
0, 1.
Yes. If you're Q0 and you see an A, you can either stay in Q0 or you can go to Q1. So it's as if you could go to, you take the union of those two, whatever they can reach, and you will go to the state 0, 1. Right. Now let's say you're in 0 and you see a B, where should you go?
At 0.
Yeah. Let's say you're in state 1 and you see an A, where should you go?
State 2.
Say state A and you see a B, where do you go?
Stay at 1.
There is no loop here though. This is a trick question as well. So
Implicitly rejected.
yeah, you implicitly reject from Q1. So what we say is that the NFA is in no states simultaneously. So we go to the set of no states. Let's say you're at Q2 and you see an A, where do you go?
Go to the set of no states.
What if you see a B?
Same.
Let's say you're in state, okay, we did the singletons. Let's do 0, 2. Let's say you're in state 0 and 2 at the same time. And you see an A. You see an A, Q0 is gonna stay in Q0, but Q2 is gonna implicitly reject. So it's going to be, the transitions from Q0, which is Q0, union the implicit rejection from Q2, which is the empty set. So what you're just gonna be in is just Q0. So you go from 0, 2, when you see an A, you're gonna go to Q0. Double check me on this as well. All right. Now let's say you're in Q0, if you're in 0 and 2 at the same time, yes?
How would you get to 0, 2 in, like what process leads to that, or is that just?
We'll have to see. Once we finish all the transitions, some parts are right now missing. For example, you cannot enter 0, 1, 2 because we don't have anything in there yet. Once we finish the transitions though, we'll talk about that. But let's finish the 6 something left, right? If you're in 0, 2 and you see a B, where do you go?
Still 0.
Not quite. Wait. What? You implicitly reject from Q2, and then in Q0 you stay. I guess that's correct, but now I'm off my memory. Okay, fine. Okay, let's say you're at 0, 1, 2. Let's do 1, 2 first. Let's say you're at these 3 states simultaneously. Excuse me, these 2 states simultaneously. And you see an A, where do you go?
2.
Correct. 1 will go to 2, and 2 will implicitly reject out. So you're stuck at 2. And let's say you see a B at 1 and 2. What do you do?
Empty set.
Yeah, both states are going to implicitly reject. Okay? Now, let's say we're in all 3 states simultaneously. We're in every state at the same time. 0, 1, and 2. We're here. Where should we go? Actually, I forgot 0, 1. My bad. 0, 1. Let's say we're in 0, 1 at the same time. If we see an A, where do we go? Q1 will implicitly reject. Q0 goes to Q1. So 0, 1 will go where?
1,
0, 1, 2.
Yes. On an A. Yes. Yeah, so Q0 stays in Q0. Q0 also goes to Q1, and then Q1 goes to Q2. So if you're in 0 and 1, you go to 0, 1, and 2. Okay, I think I made a mistake on that one. But now let's say you're in 0, 1 and you see a B, where do you go?
0.
Yes. Q0 will stay in Q0, but Q1 will implicitly reject. So that's going to be B. Okay? And then, finally, let's say we're in all 3 states at the same time. Where do we go if we see an A? Okay? If we're in all 3 states at the same time and we see an A, This will implicitly reject. This will get you in Q2. This will get you in 0, 1, 0, and 1. So if you're in 0, you're in 0 and 1. If you're in 1, you're in 2. And if you're in 2, you're nowhere. So you're in 0, 1, and 2, right? The union of those. Finally, if you're in 0, 1, 2, and you see a B, where do you go?
0.
All right, we did it. Almost done. Final states. Which states are accepting? Yes.
Any state with a 2?
Correct. That one, that one, that one, that one. Okay, we did it. We built the we built a DFA that correctly simulates this NFA. There are some problems with it, though. What are the problems with this DFA?
You never get to 0, 2.
Yeah, so this state has no entrance. Think of it as in a graph sense. If you have no entry in a directed graph, I mean, this is why even have such a node. So first off, that doesn't do anything. Okay, what else?
Disconnected.
Yeah, there's a little disconnected component here. You could clearly draw a line and make a cut. You can't ever enter 1. You can't ever, if you can only enter 2 from 1, but you can't enter 1. No, you can't enter 1, 2. You can't enter 1. And those are the only ways to enter 2. So you can't enter 2. And those 3 are the only ways to enter the empty set. So you can't enter that either. This whole thing is garbage. Okay? Let's rewrite the NFA. Let's rewrite the DFA now into just the parts that are remaining. Okay. Honestly, that looks pretty simple. That looks kind of like the DFA. If I asked you to write a DFA for this language, this might have been one you would have come up with. And contrast the DFA after the cleanup part, how it looks different than the original NFA. What's really so different about it? The non-determinism has been fixed, and instead it's basically done all the try-catch nonsense. If you think of a DFA, like in terms of programming languages, every if statement must have an else. All cases must be defined. Implicit reject doesn't have that. But we need to have that here. So all the other transitions have that. And notice that basically like any state, if you see a B, it's like a reset. Just try again, start from the beginning. If you see 2 A's, you advance. If you see 1 A, you advance to here. You see 2 A's, you advance to here. And as long as you see A's, you stay there until you see a B, and then you reset, right? What else could we say? So here we were able to simplify the NFA quite a lot. Down to, the DFA originally was big, and a lot of it we were able to clean up and just like get rid of, right? So in some cases, it's not the case that the DFA will be exponentially bigger because you can just kind of like wipe it down and end up with something the same size. So sometimes the DFA is not bigger than the NFA, right? Questions on this specific construction? Okay, and again, I want to emphasize, it's not actually about the, can you do the construction? Like, you don't need to memorize this or anything. It's conceptually the way you can de-non-deterministify something. You can simulate non-determinism with a blow up to the number of states, but you can do so deterministically, right? Questions on that? I'll give you one last kind of hurrah. There are, in fact, NFAs that are provably exponentially worse there are DFAs that are provably exponentially worse than their NFAs, right? So let's suppose we had W's in sigma star. W has an A, N from the right. So what this means is A right? It is exactly N symbols from the right. DFA, though, forced to read left to right. NFA can solve this problem easy. What's the NFA for this problem? Yes.
Would it just be two nodes where the first one loops back A, B, and then the next one is A?
Not quite, not quite. This is also a tricky one, I think. In fact, it's provably like the most efficient use of non-determinism. I'll tell you guys, the answer is you just guess when you're gonna see the A. Right? You see the A, and then you just take exactly n more states, n more transitions. So guess the prefix, just not in terms of guess this part, read an A, and then just take exactly n symbols, but count the n. You need to make sure it's exactly n from the right. How many states does such an NF, this is an NFA, right? How many states does such an NFA have?
N+1.
Yeah, it's gonna be n plus 1. Now, how would you do this deterministically? How would you do this with an algorithm, first of all? Suppose you have an algorithm that also can only loop left to right. How would you write a program for this? Yeah.
Just have,
Oh,
Go ahead.
I was just gonna say, have the loop start from right to left.
can't start from right to left though. That would make sense in a program, but what if I forced you to go left to right? Right to left would actually be perfect, but we can't do that. Suppose I forced you to go left to right. Yes.
Some sort of dynamic programming approach where you kind of keep track of the states as you go along.
Yeah, basically, you have to keep track of the states that you've seen. The DFA finite memory, it's gonna forget things. You need to memorize the last n symbols you saw. You need to know, did I see an A exactly n symbols ago? If that's the case, it takes a lot of states to do that. Another word you could use is sliding window. You're familiar with the sliding window. Essentially, what you do is you make one state per possible prefix of length n. So let's say QABAA, right? This would be a state. And let's say you saw an A. These are the last 4 things that you saw, right? And this, you only enter the state upon seeing an A. So if you see an A, what you would do is you would transition to a new state, QBAAA, right? As you see an A, you would forget about the A you saw 4 ago, and then remember that you saw BAA. So the sliding window here would be like this, right? That's the same BAA here, right? And then if you saw a B from this state, you would do Q BAAB, right? And those are the same B's remembered. So in that way, you can keep track of you make a lot of states. You keep track of the last 4 states that you saw. This is the DFA technique, and it's so big I can't even write it down. How many states does this DFA take?
It's the alphabet size to the power of, no, it's
Yeah.
2 to the power of n,
Yeah.
isn't it?
So it's actually exponentially more states than the DFA. Now the question is, can you decide this language deterministically any smaller? Certainly by the Powerset construction, there's 2 to the n plus 1, okay? This one has 2 to the n. Can you do it any smaller? N squared, n 2n, who knows? The answer is actually no, and you can prove this. You can actually prove that you need to memorize. You need to have 1 state per possible string of length 4. Here, in this one, it's only 4, but suppose it's n. The reason for that is if you suppose you had 2 to the n minus 1 states or something, there is a string input that'll allow you to make a mistake. Because you will forget something that you're supposed to remember. Something like this. That's sort of how the proof goes. But you can prove that the DFAs are exponentially worse than NFAs and that the Powerset construction sometimes is actually optimal. The Powerset construction is actually what is the best DFA. But not always. Right. More questions? All right.